discover it as these objects are practically in a one-to-one, they're co-rotating with the Earth. And so if you discover it far enough, you may get about a year until it actually starts coming into, starts doing this. So if you know on average that there's one coming every year, you can plan a mission for whatever is going to be up there at that point. And the last thing that I show these because these are kind of entertaining, but I don't recommend this as an investment quite yet. There is potentially money to be made here, maybe not by us, but by our children and grandchildren. Asteroids are a source of resources. You might think platinum and gold and things like that, but it's actually water. Water is hard to get into orbit, and some of these may be water rich. There are companies that are actually trying to do that, and I thought this was rather ambitious until I went to a couple of conferences and saw a little bit of their math, and now I think it's a bit less ambitious than I used to think of. So this is something that might work out in about 20, 30 years.
What's the evidence that these are water rich?
Spectrum. You can see spectral lines of water in some of them. And here's a nice animation with asteroids tagged by their value. So there's one that's apparently $5 trillion of platinum worth. Okay, so what do we want to do? We want to identify and map the orbits of the small bodies in the solar system, because we want to understand the evolution of the solar system, we want to be able to warn us of the hazardous ones, and ultimately, in the long run, find the valuable ones. And to do that, we need two things. We need fast, large telescopes to enable data collection. And then the second challenge is, once you have the data, can you actually identify asteroids as such? And so this is a cue for me to introduce LSST. So LSST will be a deep, wide, fast optical survey of the sky done with an 8.4 meter telescope that's currently built in Chile. It will cover about half the sky, so southern sky, to about 24th magnitude, 24.5. Over 10 years, the depth is going to build up to about 27 and a half. Precise photometry, precise astrometry, large camera, about 15 terabytes of imaging data per night, and in the end we get a total of about 40 billion static objects and about 6 million solar system objects.
What's going to get at the magnitude?
Coaddition. So every location in the sky is going to be reobserved about 800 times, or in 6 bands. So in one band, about 200 times. So if you co-add those, you get up about 3 magnitudes. So LSST has recently been renamed, and this has been a long time in the making. It's a fantastic name for this new observatory. So the new name is Vera C. Rubin, the NSF Vera C. Rubin Observatory. Things are a little bit more complicated than that, unfortunately. So now the LSST is known as the Vera C. Rubin Observatory. The actual program, the 10-year survey that we're going to conduct, is called the Legacy Survey of Space and Time, being executed in the Vera C. Rubin Observatory using the Simone Survey Telescope with the DOE LSST camera. So every time I manage to get that right, I give myself a pat on the back. We did try to keep LSST as an acronym just for historical reasons for the survey, but I think Vera Rubin really deserved this. She's one of the first, one of the early not proponents, but people who have really identified strong evidence, in addition to wikis, for dark matter. And one of the things that this telescope is going to do, in addition to finding asteroids, is do a lot of fundamental physics, dark energy, dark matter, and so forth. LSST is being built in Chile, as I mentioned. This is the site. If you've been down to CTIO, it's a few kilometers away. This is a site a couple of years ago. This is us blowing up the top of the mountain. It's fun. You don't get to do those kinds of things usually as an astronomer. This is this site in 2014 with a deputy director doing things he's not allowed to do. It's a big hole in the ground. This is the site as of a few months ago. So this observatory is really being built up, and right now the cladding is being put on top of the dome. And in about a year, this is what it's going to look like. So this to me is one of the most impressive things about LSST, that I've been staring at this for about 10 years now, and seeing it on the mountain and looking almost exactly the same as in that rendering is just brilliant. Inside the dome is this 8.4 meter telescope, 6.7 meter effective. The unique thing about this telescope is that it's very fast. Although it has an 8 meter diameter mirror, it can slew and settle to the next field in about 5 seconds. So it spends most of its time actually staring at the sky. And this is the telescope for real. So this has been built at Asteroids in Spain, put together, tested, disassembled, and sent back to the mountain. And right now it's at the mountaintop waiting for assembly. In the center is the camera. Camera has 3.2 gigapixels. This is kind of a rough scale, so it's a big piece. And it'll be the largest astronomical camera, optical camera when built. That should come in soon. We'll soon have an announcement that the camera has been assembled. It's really nearly complete. Here you see a photograph of all the individual CCDs lined up in the camera, and this down here is the L1 lens. This is the lens that comes at the front of the camera window. So that lens is about 1 meter across, to give you a scale. When I was in high school, they taught us that the biggest refracting telescope has about a meter-sized lens, and then everybody moved to refractors. So it's kind of funny to see that now we have this lens on the camera as the entry point into the Dewar window. That's of that size. It's brilliant. And here's where we are in the timeline. And here's where we get the first light with commissioning camera. So it's about 1 year and 2-3 months away. And then in less than 2 years, the big camera goes into the telescope, and the survey begins in October 2022. So we're about 2.5 years away from and change away from observations, and that goes by very, very quickly.
Will the data be recorded or just the fraction?
Everything will be stored. Everything.
Big enough computers?
Yes. That was early on in the project. The assumption was that we wouldn't be able to do that, but one of the upsides of waiting for a long time to get into the funding queue is that technology catches up with you, and then you can do things you couldn't do before. So it's good. So we will have the telescope to give us the observations in something like 2.5 years. And we'll actually have first observations in a year and change. So how do we map the solar system with this? How do we find asteroids? So I'll make this a bit of an audience participation challenge. So here's a photo of the sky. Can anyone point at the asteroid?
It's supposed to have a streak to it, is that the key, or is it just red?
If you're able to point to one, then you should go play the lottery, because it's this one. They look exactly like stars. The hint is in the name.
What is the exposure time?
This is a fairly short exposure time. It's similar to what LSST is going to do, but even with longer exposure times, most asteroids do not streak. So they're actually, the vast majority of them are just dots. So you can't tell based on a single exposure of whether you have one or not, unless you compare to a different image that you've taken previously. And even then, you might not know whether this is an asteroid or whether this is some object that just popped up there, the flaring M dwarf or something like that. So the way you find out that this is an asteroid is you take 2 images in quick succession. When I say quick, I mean minutes.
You mean what?
Minutes, in a couple of minutes. So then you see, apologies, this is not a great, I'm not sure if you can see, there's one here, and there's a dot kind of roughly the same magnitude down here. So you see 2 objects that are close to each other, or you see 2 detections that are close to each other that statistically are likely to come from the same object and likely to be an asteroid. So this is how traditionally this has been done. You take 2 exposures, you blink them, you look at things that move, and you say, oh, that's my asteroid, and now I know the direction of motion because I can draw a little vector between the 2 points. That's not enough to determine the orbit. So what you do is you come back next night and the next night, and a couple of nights later, you've accumulated enough data, say a pair in the first night, pair in the second night, pair, to be able to solve for the orbit, and then you've discovered your asteroid. And then you go and repeat that 5 million times. The challenge here is when you go deeper, the image that I showed you here is fairly shallow. This is actually an amateur, taken with an amateur telescope. So it really is shallow. I think this is like 18th magnitude, 20 magnitude, something like that. You take the LSST, it goes down to 24th magnitude, you position it at the ecliptic, and you look at the field of LSST, you see about 5,000 asteroids in each field, each 10-degree field. So then you start having a problem, because you take an image, you come back, say 30 minutes later, all of those asteroids have moved, and they may have moved actually sufficiently so it's ambiguous which one is which. Then on top of that, we're doing image differencing, we're doing some relatively complex image processing that can occasionally introduce artifacts. So now you have these artifacts popping up that are occluding your judgment about what's going on here. And a typical solution to that is, instead of coming back once, you come back the second time or the third time. And now you have something that looks like this. You have a row of detections that you can draw a line through and use as a filter against artifacts, against confusion, and so forth. So this is how most surveys operate today. But the issue with this is that you reduce your efficiency. So now I've built this $500 million machine where I'm observing a quarter or a half